3.5 is on derivatives of trig functions. So these are the key functions you need to know for trig. So basically, sine, cosine, tangent, cosecant, secant, and cotangent, all the 6 major derivatives. So I would say, at least for Calc 1, you should have these pretty memorized to help you do all the problems. Obviously, you can look them up, but you can't, if you can't be looking up sine and cosine especially, and frankly tangent as well. So those you just need to know and not just memorize. Like, you just got to know. Derivative of sine is cosine. Derivative of cosine is minus the sine. So we'll see one proof of this, and the rest are done similarly and using other identities to prove them. So before I get started on the proof, we need a couple of identities we'll be using and another limit, and then I'll show you the proof. And then we'll look at a couple examples. So first one we're going to use here is, so we want to prove d dx of sine x cosine x. We're going to need this sum formula. So the sum formula for sine and cosine. So you have, alpha plus beta, and this is how you'd expand it out. We're going to be using x and h, so I showed it in terms of x and h for our limit, for our definition of derivative. So sine of x plus h is sine x cosine h plus cosine h sine h. So that's an identity. I wouldn't expect you to know that identity. You'd look those up. I don't remember any of those. But I know there's a sum formula, there's a difference, there's a double angle, that kind of stuff. So speaking of double angle, here's another one. All right, so first we need to talk about this limit, the limit of cosine y, and I'm just putting in different variables. We'll use x and h, but the limit of cosine y minus 1 all over y as y approaches 0. So what does that equal? Well, it turns out on page 69, example 5a goes through this little example of what it is, using basically sine theta over theta as our major theorem that's not using other limits. All right, so to do this, we use the half angle formula, and that cosine y can be written like this. And so you have the limit of cosine y minus 1 over y. And then if you substitute here for cosine y, the 1's will be 0. So we end up with a negative sine squared over y over 2, and then all over y right there, like that. So then we have y over 2 in the inside, and then when we do that, everything's going to 0 anyway. So we can still let theta be y over 2. So then y is 2 theta. So if you substitute y over 2, this ends up being theta, and then this ends up being 2 theta, which reduces that 2. Once you do that substitution, the negative can factor out, and then you end up getting this nice form. Well, we know that limit of sine theta over theta is 1, and limit of sine theta is 0. So this ends up going to 0. So not an obvious one, really. You end up getting, this is indeterminate. So 0, you end up getting 0 over 0 because cosine goes to 1 as y approaches 0. So, oops. Okay, so we're going to use that here in a bit. So here's the proof. So that's all stuff ahead of that question. And let's look at the proof now. So we're showing that d dx of sine x is cosine x. All right. So, proof, so dx of sine x is equal to the limit of f of x plus h minus f of x. So we're going to say that is then sine of h plus x minus sine x all over h. And I think I put it in that order on purpose. Maybe I didn't. No, write that as, it doesn't matter obviously, right? But I actually do want it x plus h to mimic the form above as h approaches 0. So this is where now we're going to expand sine x plus h using the formula above, using the sum formula for sine. And we get that this is equal to the limit as h approaches 0. And then let's expand that out. Not real sure how long it is. So it's sine x cosine h plus cosine x sine h minus sine x all over h. So then we factor out right here sine x. Factor out sine x here and here and rearrange terms. So this is equal to the limit as h approaches 0 sine x, and then that's times cosine h minus 1 plus cosine x sine h all over h, which equals the limit as h approaches 0. And now we can look at these limits. So this is going to be sine x, and then you end up having cosine h minus 1 over h plus, and then we'll just keep this the same for now, but that's going to 0, or I'm sorry, to 1, over h. I was breaking this up on purpose like this. So you can rearrange that and write that as basically sine x, because there's no h in there, you can just take it out, times the limit as h approaches 0, cosine h minus 1 over h, plus cosine x times the limit sine h over h as h approaches 0. And we can see there that this, didn't mean to do that one, that's going to, okay, this is approaching 0, and this is approaching 1. So what are you left with? You're left with exactly cosine x. Okay. So we're not going to, you can look at, there's other proofs, I think, in the book, but that's one of the most important ones to show, and the rest are done in a similar way. Okay, so that's the whole thing right there. And then, so the other one, after that, you need to know what those derivatives are. So basically, derivative of sine is cosine. Derivative of cosine is minus the sine. They have to go back and forth, basically. Okay. So the next thing I want to take a look at is higher order derivatives, like basically the notation for higher order derivatives. And so I'll just write it like that. Notation for higher order derivatives. That didn't work. Okay, so if you have y equal to f of x, then we can write y prime is f prime of x. So there's the prime notation. We can also write dy dx, or this stuff I already showed you, d dx of f of x. That form is like it's like an operator. It's kind of like showing you perform that operation on f of x. These are more like they are the derivative. It's subtle. There's not really a big difference there. And then we had the dx of like y or something. Okay. Then if you do, now you can do it again. So if I say y double prime, it's f double prime of x. And this notation gets a little weird, but it's, you say d2y over dx squared. You could also write it as d squared over dx squared of something, of, say, f of x. Another notation. And then you keep going. You could say y triple prime is f triple prime. That's as far as you usually go. You don't usually go 4. And so that would be d cubed y over dx cubed. And then you can write d cubed over dx cubed of something, of f of x. And then in general, you can write it as y, and then you put in parentheses in. That's like the nth derivative of y. So it's f in nth derivative of x, or we'll just write dny over dx to the n. So you would say, like, the 15th derivative of y is what that would mean. That doesn't mean y to the 15th. In practice, though, we really don't go past that. You could write maybe a 4, 5. Normally, just if you're going to express it as a general statement, you put in the in like that. And just an FYI, in Calc 3, you end up doing derivatives, or what they call partial derivatives, and then this order down here will matter. So you can say, you'll say something like, d, let's see, it's like dy, and then you could end up saying, oh, they're partials, and then they have different orders of y. That would basically mean you do z first, then y, then x of, say, f of something, f of x, y, z. So the denominator matters, but for now it doesn't, we're just doing multiple derivatives, so I wouldn't worry about it. Okay, so then look at some examples of just taking derivatives and product rules and stuff like that. So let's take a look at that. So examples. So this is where I'd have you try it. So I want you to try these. So we let f of x be x squared sine x. What's the derivative of that going to be? And you can see that this requires a product rule, right? Because you have that function, and then you have this function. So you have x squared and then sine x, and so it needs a product rule. So f prime of x is equal to derivative of the first times the second plus the first times the derivative of the second. So now this is what's new. The derivative of sine is cosine. And sometimes you can simplify that, sometimes you can't, but that would be it. Okay, so maybe try, I'm not going to write it up, try f double prime of x. So if you do f double prime, this requires a product rule, and this requires a product rule. So it'll be basically, you end up with 4 different terms. Okay, so try that. So it's a little messy, but go for it. The next example. What if I have f of theta equal to sine theta over 1 minus cosine theta? Okay, so then you want to apply what rule? The division one, that's the quotient rule. So apply the quotient rule. Okay, so df d theta is equal to, and so just go through it. So try that. Okay, so try it, pause it, see what you get. Okay, so derivative of the first, so I'm going to go all the way like that. Derivative of the first times the bottom minus the first times the derivative of the bottom. So that'll be 0, I'll write it all out, 0 minus negative sine theta all over 1 minus cosine theta quantity squared. And in this case, I'm guessing something's going to simplify. I don't know, but you do want to try to expand these out. In the long run, in the couple next chapter really, you're going to, you're going to be setting these equal to 0 and solving, whereas the denominator is 0, that kind of stuff. So we do want to get the hang of it. It turns out this one does simplify. I worked this one out. So you get cosine theta minus cosine squared theta. And then that next is just what? That's just a negative sine squared theta all over 1 minus cosine theta quantity squared. Don't need that big long division bar now, do I? So let's erase some of it. And let's go ahead and I'll go across here because you can actually see that this simplifies pretty nicely. You get cosine theta minus, so you factor the negative 1 out, so you just get 1 over 1 minus cosine theta quantity squared. That's the Pythagorean identity. So we basically used cosine squared theta plus sine squared theta equal to 1. We use that right here after factoring out the negative 1. Okay, so check that out. But so now the top's almost the bottom, but you gotta flip it and take out a negative. So it's equal to negative 1 times 1 minus cosine theta over 1 minus cosine theta quantity squared. So you end up getting basically negative, or negative 1 on top, and then 1 minus cosine theta on the bottom. Simplifies quite nicely. So basically here for domain type issues, theta cannot equal what? Cannot equal 0, because you get a 0 denominator, and then it's never 0 either. That's the other important idea here, because the numerator is always just 1. There's no variable up there. That's the type of stuff we have to analyze eventually. Okay, so one more. Try this one. So suppose you have f of x equal to, we'll just put in tangent x, root x. Okay, so try that one. Okay, this just first derivative. Okay, so I'm not going to work it out, but it requires product rule. And I got 2x secant squared x plus tangent x all over 2 root x. So if you combine it in the end, that's what I ended up getting. Because when you do the the derivative of so if you have like root x, then y prime is 1/2 x to the negative 1/2. So it always comes down in the denominator. Okay, so there's a lot more stuff in 3.5, but that's really the key areas to look at. And make sure you know what the notation is of multiple derivatives, and then all of those trig functions there.